Hello, my name is George Paris. I'm a PhD chemist, and I am here to bring you a new idea today. We have formed a company called Directed Energy Materials. And you may wonder, what is a directed energy material? Well, going back all the way to my graduate days, I had the idea that we should be able to take material, for example, a resin, and we should be able to project energy into that material in such a way that we cause the material to undergo a chemical reaction and go, for example, from a liquid to a solid. And that without having forms or molds or other types of devices, other types of tools, we could use the energy itself as a tool for creating new structures from a medium, for example, a resin. So let me hit that a little bit harder here with an example, some graphics. Here we're sending energy into a medium, and the energy is such that it creates a solid, a something physical that we can isolate. And we can continue doing this as we go along. To map out a material that we wanted to be able to isolate. And so this is sort of the concept of directed energy materials. We're using the energy as a sculpting tool to create materials, right? So this is effectively a method of additive manufacturing. And at the bottom of this little graphic here, we have my email address. It's antimony, A-N-T-I-M-O-N-Y. That's chemical element _121 at hotmail.com. Okay? So if you want to get in touch with me about any of the technology or intellectual property that we're about to talk about, either as a potential user of that material, or if you are interested potentially investing in a startup company, you can contact me and we will talk about it. So going back a little bit, Directed Energy Materials LLC was founded to develop new methods of additive manufacture and capture the intellectual property defining those technologies. In particular, we're interested in technologies that can accomplish unique tasks not addressed by conventional 3D printing, casting, molding, welding, plating, milling, engraving, etc. Okay? To this end, we have ongoing research and development in mechanical, electrical, and medical fields. Our business plan is to license our intellectual property and collaborate with our clients. Here again, you have my phone number. If you call me, I'll try to be civil when I answer. I get lots of strange phone calls, but I'll try make sure that you let me know early in the conversation what you're interested in, and we will have a pleasant conversation. Okay, let's talk about the intellectual property. We currently have 2 issued patents, okay, and we have probably a half a dozen other patents of various things in process. Some of these are going to be provisional patents, but most of them are patents that have actually gone through some sort of review process, and we're haggling with the examiners over what claims to accept, which claims that they will agree to. All right. So I would say that I'm very confident that almost everything that we have claimed will, one way or the other, show up in a patent that we will have as intellectual property in the near future. This gives you an idea of what we've got. Okay. Basically, this patent was issued December 27th, 2022, a little over about a year and a half ago. The title of it is Bragg Peak Three-Dimensional Manufacturing with Resins. Now, basically, if you shoot a proton beam into a liquid resin, you're covered by our patent, which you'll find out is a very broad area. Now, most of you probably are not very familiar with or conversant with the idea of proton beams or something called the Bragg peak. Well, the Bragg peak goes back to the early 1900s There were a father-son brag team who discovered that you sent a particle flying into a medium that its energy bleeds off. It has kinetic energy. We're talking about millions of electron volts of kinetic energy and a proton, and that flies into a medium and it penetrates. Now, it turns out that the linear energy transfer, that is to say, the energy that kinetic energy from the particle lost to the medium, increases as the particle slows down. As a matter of fact, the function is roughly 1 over the velocity. So as the proton approaches zero velocity, it's dumping all of its energy into the medium. And that's what we call the Bragg peak. So the irony here, the unusual part of this, the counterintuitive issue here, is that the energy is not delivered to the surface. You probably are familiar with X-rays or UV, where the surface is the first thing that gets hit and is most highly impacted. That's not what happens here. The energy is delivered inside the medium at some depth that can be calculated very accurately, as we'll show you in a moment. In any event, the concept, this is actually from the patent, the drawing I have here. If you had a container of, say, resin, that would be number 1 in this scheme, and you fired a proton beam, that would be number 2, coming in from the left into this resin, it would lose energy, and it would lose energy more quickly as it slowed down. And what we show here, the point number 3, is actually what we would call the Bragg peak. And that's where the energy density is greatest, and that's where the likelihood of causing the polymerization of a resin is maximized. And so you get a solid formed in the middle of this liquid resin all by itself. And we use that technology, and we'll show you some nice examples a little later. But if you are doing this, you're in our patent one way or the other. Okay, the first patent we actually tried to get took us about, I don't know, 5-7 years, something like that. And it had to do with this all started, I got interested in carbon. I got interested in carbon nanotubes, graphene, stuff like that. And I discovered that the physicists that sort of drive this wagon were starting with methane. And I'm like, I'm an organic chemist. You tell me that you're going to make graphene out of methane, and I go crazy. Why not start with a polymer that you can easily convert into pure carbon? And it turns out that our friends at Dow Chemical Company long ago made a material called, they called it Saran. It was actually polyvinylidene chloride, which is a polymer of 1,1-dichloroethane, or ethene, or ethylene if you're an engineer. And so this polymer, it turns out, the irony here is you can't buy it anymore because the starting material, the 1,1-dichloroethene, goes up and creates havoc with the ozone. But we have not done any experiments with it because we don't have the material. But there are other items and other possibilities here. And of course, if you contain the 1,1-dichloroethylene, ethene, you could avoid some of these issues that the mass production of Saran, which was the trade name of this material, would cause. Now, what we're looking at here, if you take the Saran, or the polymer, and heat it up moderately, you don't have to heat it up very hot, it will undergo a typical elimination reaction. A chlorine and hydrogen will split out, and you will end up with, eventually you'll just end up with something that could look like polyacetylene. What it actually happens is anybody's guess, But it's a very clean reaction. All the hydrochloric acid comes out of the system, and you get some of the purest carbon you can probably ever make. Now, the idea here was we wanted to make a electrically conducting carbon, and it's almost dead certain that we're getting a an olefinic, that is to say, an sp2 hybridized carbon out of this. And so we should be conducting electricity. And we thought, gee, we can do this and we can deposit the carbon along with other elements. For example, we can deposit boron, we can deposit nitrogen, we can deposit phosphorus, we can deposit arsenic, or we can deposit iron, we can deposit chromium, some other elements, manganese. So we can deposit almost any element we want to, given our understanding of the chemistry, with the carbon and produce carbon-containing compounds or carbon-containing polymers that have all sorts of electrical conducting properties. And we think this might be very useful in a very wide number of areas, semiconductors, capacitors, etc. And we can do it on a very tiny scale because we're using a laser beam here, which we can focus down very finely and make your carbon do what you want it to do. Okay, so this patent actually had several iterations, and we are still, although it has been issued with certain claims approved, we have a whole nother set of claims that are still built in, and we're still arguing with the Patent and Trademark Office about those claims, and we have a very good idea that they're going to be approved. Okay, let's give you an example of this proton beam stuff. And I keep showing up down here in the lower left right-hand corner. That's not supposed to be happening. But, in fact, I'm not supposed to be in this slide at all. I wonder how that happened. In any event, what you're looking at here is a step-by-step process. It turns out, by the way, that I am obscuring a view of the proton beam generator that is coming flying down here and hitting the skull. Maybe I need to have my brain tumor taken out. But anyway, on the left-hand side here, you see a example of a skull. This is a anatomically correct plastic skull. This is not some person we decapitated. And we have a plastic sphere with a set of index markers. These are actually little balsa wood sticks we've managed to create inside the sphere. And if you go up to the top, we've put a resin, liquid resin, into this mix, and you can sort of see the opalescence inside the sphere. And then when we send a proton beam into this skull, which goes through the skull, through the packing material around the sphere, through the plastic sphere, and into the resin, it eventually dumps a bunch of energy at the Bragg peak. And you have here at the lower center part, you have an example of a what would be called a phantom. Now, all of this work was done at the Maryland Proton Treatment Center. Some very cooperative and collegial guys up there, physicists, who are interested in dosimetry and making phantoms of proton beam treatments. And that's basically what we've done here. We have the medical field calls phantoms essentially a physical object that looks like something you're trying to do medically. So what we have done here is we have created a representation, that is to say that blue blob in the middle of that sphere that's actually was targeted right on that index markers. And we hit our mark, obviously. And the phantom basically represents the energy delivered to the system. Now, this is the only example I am aware of where you could show a patient that, yeah, we're really going to shoot this proton beam into your head. It is really going to go through your skull and not do any damage. It's going to go through most of your brain and not do any damage. It's going to hit the cancer, the tumor that's in the middle of your skull, and it's going to kill the tumor without destroying your brain. Now, that is a counterintuitive phenomena, which this actually demonstrates. This is a physical demonstration of that process. And this is the only physical demonstration I'm aware of. Most of the time, they talk to patients, they show them graphs of the energy, linear energy transfer, and they talk about the Bragg peak and all that sort of stuff. They show them some cartoons. This is not a cartoon. This is real life. This is something that actually was created by shooting a proton beam through the skull, through the plastic, through the resin, and creating a energy field right where we wanted it, right where we targeted it. Okay. Now, we have looked at some other options for doing medical related things. It turns out that most people were just focusing on cancer. One of the reasons for doing that is that the proton beam is expensive to create. You have to have a cyclotron or a linear accelerator of some sort. It's a big deal to do that. And so it costs much money to get your cancer cured with a proton beam. Now, part of our motivation here is if we can make the proton beam a manufacturing tool so that we're punching out widgets 24/7, 365, we can make the use of this technology much less expensive. And you could have a dual use facility where on one side you've got a manufacturing site, and the other side you've got a clinical facility, and you just send the beam where you want it. And that would make the marginal cost of proton beam treatment very low. And you could use it to do all sorts of other things that would not be as critical as treating a brain tumor in some child. You know, people are willing to spend an incredible amount of money to treat a brain tumor in a young child. And that's sort of where we're at right now. But what we're trying to do conceptually is bring proton beam technology into a manufacturing environment, reducing the cost of its stuff, and not only make the cancer treatments cheaper, but also open up the screens for other applications in the medical field. And so we've been doing some work here. I'm not going to tell you exactly what this is. If you're smart, you can figure it out. But the medical applications of proton beams, we have, this is a patent pending situation. We have gone beyond the provisional patent application process here. We have ongoing research, and hopefully within the next year we will have a full patent, probably not issued, but at least submitted. But we already have provisional patents and beyond going on right now. So let me go to the next one. This is, we were talking manufacturing. That was where we came into this. We really sort of got dragged into the medical field because that's where the proton beams were. But in terms of manufacturing, these are some examples. Starting on the upper left-hand corner here, we have a plastic box. Inside that plastic box, we have a metal frame, and sandwiched between the two pieces of this metal frame, we have a stack of aluminum screens, very fine aluminum screens. You can't see the little holes, but there are holes in this aluminum screen. And we put resin inside the plastic box covering the aluminum screen, and then we actually buried this whole thing under, I don't know, 4 or 5 inches of water because we wanted to be, it was easier for us to control the slowing down process that way. And so we sent 2 shots of proton beams through there, and lo and behold, we calculated just right and were able to deliver the Bragg peak right where we wanted it. and it looks like we put a couple of nails through that, and you can't do that with any other technology that we're aware of. So the lower left-hand corner in the center, you see the screens, and then at the top, we have a profile view of this, where you see uh, the solidification of the resin only occurred where the brag peak was, and it's just like putting a couple of nails through the stack of aluminum screens. Now to the right here, we have a different situation. We're using some aluminum honeycomb, couple of pieces, and we decided we fill this container with the aluminum honeycomb and aluminum alloy powder. It's aluminum magnesium alloy, I believe, and the resin. And then we fired our proton beam through it, and this is what we got. Now, this is on our way to making metal parts. The proton, not proton, but the 3D printing process is not much different than this. We have not gone through the process of trying to extract the resin and solidify the part, but you see that we're on our way to doing that. Now, 3D printing, typical 3D printing, is a step-by-step, layer-by-layer process, and it is notoriously slow. Carbon ink has created a faster way to do it, but this, you're still doing it layer by layer. Now, what we want to do is essentially instantaneously do it. And so what we've done here is we have intersecting laser beams, and we, in a matter of a few seconds, literally a few seconds, created the two lasers, intersected the resin, and created a energy density suitable for polymerizing the resin. This was facilitated, by the way, by another one of our patent applications and technology advancements, in which we have a dye material which changes color when it undergoes this reaction with the resin. And lo and behold, you'll see in that lower left-hand corner, you'll see a very faint purple or blue color in the shape of a donut. And using that as a guide, we use that to tell us when to stop. And it literally was a matter of seconds that we had to do this. And we were able to come in here with a probe and pull out the solid. Once we managed to drain the resin off of the solid, we have this piece on our right here, which I'm partially obscuring. But it's a hard, fine material. And this was actually, I think, the first experiment we did in this technology. Here's, let's see if yep, here come the laser beams. Go from there to the solid, get rid of the excess liquid, and you have the solid material that you can use. Okay, along these same lines, we've got some other examples here. This object on the right and the upper left, that's a two-part series. One's a cylinder, and one is a disc. They were created simultaneously using two laser beams. And the two laser beams basically intersected, and we cured this a little bit longer. We actually, this took probably about a minute to do this, and we created this shape. It's just used as an example of the type of thing that we can do. It is certainly not the limitation of what we can do. All of this, by the way, is patent pending. We've got patents applied. Now, we are not just a bunch of cowboys out here. We do make quantitative experimental measurements. We accumulate our data. We put it together in publications. We have all of our records. We are filing patents left and right. This gives you an idea of what we've been doing. We also like to think outside the box. We do not think of ourselves as limited by what people have done in the past. We are not tied to 3D printing in the normal sense. We are tied to new and great adventures. We get our hands dirty. We don't mind getting in the lab and working through things, figure out how to make it work. And the important thing here is we're just getting started. Okay. The company has been formed about 3 years, I believe. It's had remarkable successes in a variety of areas. We think that we have lots of technology already on the board, which is already patented, which would be useful to various people doing various types of manufacturing processes. We think that we have patent pending on a number of additional technologies, which would also be very valuable in the electrical, mechanical, and medical areas. And we believe that eventually this will be a very valuable set of patents that we hold. And in the meantime, we are looking forward to hearing from people who would like to investigate the use of our technology. And we are also willing to talk to investors. If you happen to be an investor who would like to get involved with a startup company, give me a call, send me an email. Don't send me, well, you could send me a text, but I don't really deal with text very much. But anyway, so keep in touch. Tell all your friends, and I hope to hear from you soon. George Paris, Directed Energy Technologies. Have a great day.